In this video, we will explore how a buffer solution actually works and how it is capable of resisting pH changes when a small amount of base or small amount of an acid is added to it. So, this is what I call the language part of answering the buffer solution. In the next video, you'll see how mathematically you can explore how a buffer solution actually works. But this is the one that is critical in making sure you can score the 2 marks when this question is asked in the exam. So what do we have here? We have a beaker of solution that contains an unionized weak acid Ha as well as its conjugate base A-. So let's count the number of let's count the concentration of each of them first. So we have 1, 2, 3, 4, 5, 6. We have 6 Ha to begin with, and also 6 A- to begin with as well. So let's just keep that in mind. So let's see what happens when a small amount of H plus is added into this buffer solution. Suppose yes, this happens. So naturally, what do you think would there be any reaction that happens in this? So yeah, there should be a reaction, considering that now you have a large amount of conjugate base who is capable of reacting with your H plus in the acid-base neutralization reaction. So what do you get here? Yes, when the A minus, your conjugate base reacts with your acid H plus, you will form your HA at the end of the day. And let's look at the new change. So just now initially we had 6 and 6 of HA and A minus, right? And after this H plus ion got removed in the buffer solution, now the new concentration will be 7 and 5. And 5. Oh. So 7 and 5. So technically, in this scenario, because this diagram is oversimplified, the change of HA and A minus concentration might seem to matter quite a lot, because relative to the H plus is not that big. But given in another scenario where the initial was 100 each, now supposedly you add 1 mole of H plus, so the change will be 101 and 99, which might seem like a very small deal here, when the H plus, the HA concentration increases slightly and the A minus concentration increases slightly. So what happens after that? So considering the initial amounts of HA, your weak acid, and your A minus, your conjugate base, are very large compared to the amount of H plus ions added. So focusing on this scenario here, with respect to your 1 mole of H plus, you have so much of your HA and A minus, right? The change in the ratio. So originally the ratio was 100 to 100, which equals to 1, and now the change in the ratio to the new ratio will now be 99 over 101. Will be very, very small, 0.98. So the ratio will be almost constant. So what impact does it have on the pH change? So once again, we have to bring out our pH solution for our pH equation for buffer solution, which is pH equals pKa plus log of your ratio here. So considering that your pKa or your Ka value remains constant at a certain temperature, so this is constant, and that your ratio of A minus and H plus HA, this is not constant, but considering that the change was so little, right, it's relatively constant, we can therefore say that, or conclude that your pH will be almost constant or will have changed very slightly. Okay, so likewise, suppose a small amount of base is added instead. So this time around, who do you think, or what reactions do you think will happen here? Yep, that's correct. If you guys think that your HA, your weak acid in this case, will be the one that reacts away with the small amount of base to give you your conjugate base. So once again, initially the ratio was 6 to 6. Now it is 5 to 7. And yeah, the concentration of your A minus increases slightly now, and your weak acid decreases slightly. But again, you can use the same logic. Okay, again, if this is an oversimplified diagram, so we can use the 100 to 100 initially to now become 99 to 101. So since the amount of initial concentration of your weak acid and your strong conjugate base is so large compared to the amount of OH added, right? So the OH added, yeah, the change will be so insignificant. The ratio again will be rather insignificant. So initially it was a 1-to-1 ratio, right? And now let's see the ratio of your salt over your acid, which should be 1.02. So once again, the ratio changes very little. And again, proving using the logic of the buffer equation, since your pKa is constant and if your ratio is constant, right, relatively constant, your pH will be also almost constant. As such, this answers the reason. This answers why how a buffer solution is able to resist pH changes when a small amount of acids or base is added to it. So yeah, resisting pH changes as in the pH value remains almost constant or changes very slightly. So yeah, this is the language way of explaining how a buffer solution works. So if you guys are still curious on how, like mathematically how can this pH actually change, so because now we are just talking about like general equation of using pH equals pKa plus log salt over acid. If you want to see this in action, feel free to watch the next video when we about the inquiry, when we actually look into comparing a buffer solution to a non-buffer solution, and we compare how the pH changes when acid and base is added to it. Okay, if not, come to the end of this video.